Look at this massive, sparse matrix. Early natural language processing systems, like one-hot encoding and TF-IDF, treated every word as an isolated unit. To represent a vocabulary, they created grids like this, filled almost entirely with zeros, placing a single one in the column corresponding to a specific word. Because every word occupied its own independent dimension, these models had no semantic awareness. Mathematically, the distance between the words apple and orange was identical to the distance between apple and spaceship. The continuous bag of words model, or CBOW, abandons the idea of counting static frequencies. Instead, it observes how words behave in proximity to one another to learn their relationships. Under this architecture, meaning is not assigned by human dictionaries or rigid syntactic rules. It is learned through geometric patterns of co-occurrence in the text itself. To teach a machine these relationships, engineers faced an immediate bottleneck. There are not enough human-labeled definitions in existence to train a model on the infinite combinations of human language. The solution is a technique called self-supervised learning. Self-supervised learning is a process where a model generates its own labeled training data directly from raw, unstructured input text. CBOW operationalizes this through its core predictive task. It takes a sequence of words, uses the surrounding terms as input, and attempts to infer the missing center word. By repeatedly solving this task, the model extracts infinite training pairs from everyday text. Language itself becomes the teacher. Take the sample sentence, "I like orange juice and eat eggs daily." Our first goal is to set up a predictive task. The practitioner defines a context window. A small window forces the model to learn narrow syntax and local dependencies, while a larger window allows it to capture broader semantic themes. Here is a symmetric context window of size 2 around our target center word, juice. We extract these elements. The context words become our input data, denoted as X. The center word, juice, becomes the expected output, denoted as Y. Through this simple extraction step, a static linguistic structure is transformed into a structured, solvable machine learning problem. The first mathematical step is converting the context words into one-hot encoded vectors. A one-hot vector is an array of all zeros with a single one placed at the index corresponding to a specific word, resulting in an array of dimension 1 by v, where v is the total vocabulary size. These vectors are passed to the input-to-hidden weight matrix, W. This matrix has a shape of v by n, where n is the desired embedding dimension, and is initially populated with random values. In Python, the @ symbol performs matrix multiplication, multiplying the one-hot vector by the W matrix. Because the one-hot vector contains mostly zeros, all non-matching rows cancel out. The single row matching the 1 is cleanly extracted as a simple pointer mechanism. That isolated row functions as a database lookup. It is the model's current numerical embedding for that specific word. Because our context window contains multiple words, we have multiple 1 by n dense factors extracted from the W matrix. CBOW must consolidate them. It takes these distinct context embeddings and mathematically averages them together into a single, unified hidden vector. This averaging step is why the architecture is called a bag of words. By collapsing the context vectors into a single mean, the exact sequential order of the original sentence is lost. This creates a clear trade-off. The smoothing effect allows the model to train rapidly and map common words with high precision. However, the distinct semantic signals of rare terms are heavily diluted, often drowned out by more frequent neighboring words in the window. To evaluate its prediction, the model pushes the averaged hidden vector into a second weight matrix, W'. This matrix is sized n by v, projecting the data back out to the full vocabulary size. Multiplying the hidden vector by W' produces a dense vector of raw, unnormalized scores. This diagram shows the dense score vector passing through a mathematical node labeled softmax. Softmax converts raw scores into a normalized probability distribution, ensuring all outputs sum precisely to 1.0. The result is a strict ranking. Every word in the vocabulary receives a specific probability, quantifying its likelihood of being the correct center word. The network measures its accuracy using cross-entropy loss. Cross-entropy loss is a mathematical function that calculates the distance between the model's predicted probability distribution and the actual one-hot encoded truth. This single error value is the vital signal for backpropagation. It tells the network how to adjust the weights in both matrices to reduce the error on the next pass. That forward pass is just a single event. To learn language, the model must iterate this exact process over thousands of epochs, processing millions of text pairs. During backpropagation, the gradients incrementally adjust the internal weights. Words that frequently appear in similar context windows are slowly nudged toward mathematically similar values in the matrix. This line graph shows the average loss over time. As the model learns the structural rules of the corpus, the error rate drops sharply, approaching zero near the 500 epoch mark. There is a significant distinction in how this architecture is actually used. Despite the training process we just explored, the network itself is not intended to function as a predictive engine in a final application. Once the training loop is complete, the output matrix W', the softmax function, and the predictions themselves are discarded. The prediction task was a proxy. The optimized input matrix W, the embedding space where the semantic relationships are now securely stored, is the true product of the process. In industry practice, engineers use optimized libraries like Gensim's Word2Vec to execute this exact CBOW architecture across massive datasets efficiently. Once the embeddings are extracted from the Gensim model, we use principal component analysis, or PCA. PCA is a dimensionality reduction technique that compresses high-dimensional vectors down to a readable 2D format while preserving their major structural variants. This scatter plot shows the resulting PCA mapping. Even when trained on a microcorpus, a geometric map emerges. Notice the semantic clusters. Behavioral words like eat and likes separate from food nouns, while structural words hover close to the center. CBOW demonstrated that spatial geometry can serve as the primary language of semantics. By extracting meaning from proximity rather than predefined rules, it introduced the concept of learned, dense representations that modern transformer models still rely on to process human language.